All right. We are on, we're still talking about springs, but this is sort of showing you how you could put the spring situation into the work formula. So we know that our work is force times distance, and for our spring force, we have that K times the change of distance. So we end up having this 1/2 K times the change of displacement. Sorry, so like the final displacement squared minus the initial displacement squared. And it's 1/2 because you're doing the integral. So remember, whenever you do the integral, you basically add a number to the exponent here. So this K here is a constant, so it's pulled out of the integration. And then here it would be like 1 plus 1 divided by that same number. So that's where you get this half. Okay? So it's 1/2 K times the final position squared minus 1/2 K times the initial position squared. Okay? All right, so then we go on to thermal energy. And thermal energy, these are just showing you that if you were looking at it microscopically, you would see that these atoms sort of have springs on them, and whenever they, are moving, then they are somewhat stretched or compressed, sort of like the big image of the earthquakes, with the ground and things like that. So figure A is showing you a mass moving with a velocity with a macroscopic kinetic energy. So that's basically like something that you see, like you can see with your eyes. Figure B, however, is showing you the same object but internally. So you've got the total kinetic energy of the atoms inside of it, so the microkinetic energy. And then you have the total potential energy of all of the atoms microscopically as well. And so that, if you add those two together, then that will equal your thermal energy, which we talked about right at the beginning, actually. Okay, so this one says a tow rope pulls a skier up the slope at constant speed. What energy transfer or transfers is taking place? All right, so think about it. You've got this tow rope that's pulling a skier up the slope, and it's wanting you to tell what is happening here. So if you're going up at all, you are creating potential energy, okay? What is the symbol for potential energy? U, okay? And then also, if you are pulling something up that slope, and then let's say that you let go of the skier, what's going to end up happening as far as that is concerned? Well, then you're going to be involved with kinetic. And also, by the way, you're pulling them at a speed. So there is kinetic energy that's involved there. So whenever you add the total kinetic energy and the potential energy, then you end up with thermal energy. So I would say that the correct answer here is both A and C, because you're pulling that rope up, which is causing there to be potential energy, and as you're doing that, it's causing there to be a total potential kinetic energy situation, which then whenever you're talking about the total there, then you would have to include that thermal energy. Okay, so dissipative forces, as two objects are sliding against each other, their atoms are interacting, and so you can also transfer kinetic energy into thermal energy. And you guys could do this right now if you took your hands and you moved them back and forth. You're creating friction, but you can feel that thermal energy as that's happening. And so this is just saying that if you had, for instance, in this system, a box, and you've got this rope that's pulling on it with some sort of tension. So if it's pulling on it and the box is actually moving, then you've got some kinetic friction that's involved. So this thermal energy is equal to still force times distance, but the force in this case is the kinetic friction and the change of displacement. Because think about that, could you pull on that box and it create any kind of thermal energy? Do you think there could be any kind of heat that's created right here in this area where the box is touching the ground? Absolutely. Okay, so we've got another example here of increasing kinetic and thermal energy. So a rope with 30 newtons of tension pulls a 10 kilogram crate. So I'm going to write some of this stuff as I'm reading it. So the tensional force is 30 newtons, and it's got a mass of 10 kilograms that goes a distance of 3 meters across the horizontal floor starting from rest. So that initial position is 0, and it says also that it's got a velocity of 0, that initial velocity, I guess I should say. And there's a coefficient of friction between the crate and the floor of 0.2. And so that's your mu there. And it wants to know what is the increase in thermal energy and what is the crate's final speed. Okay. So first, let's figure out what the increase of the thermal energy is. So if we kind of write our equation here as it had on that previous slide. All right, so kinetic friction is mu times normal times the change of distance. Mu normal is mass times gravity. So you've got, 4 different things here. So you've got the coefficient, which is 0.2. The mass is 10 kilograms. Of course, gravity is 9.8. The distance that it travels is 3 meters. So it goes a total of 59 joules of thermal energy. Okay. Now, it says for the second part of it, we need to figure out what the crate's final speed is. So that's the thermal energy portion. Is there some other energy that's happening? Well, we also have this tensional force here. So we have to keep that in mind too. So I'm going to actually flip over. Oh, crud, it doesn't give me enough space. Okay, so work is equal to force times distance. So we could also say tension times that displacement. So the tensional force that it gave us was 30 newtons times that same amount of distance, which was 3 meters. So we end up with 90 joules. So why am I doing that? Because there's technically a change of energy here. You've got 90 joules minus that 59 joules. Okay, that's that frictional force. So that's the opposing force. That's why I'm subtracting it, which is 31 joules total. Okay, so now it's wanting us to find the crate's final speed. Well, and what did it say that the initial speed was? It says that it was at rest. Okay, so you could technically, you could say like the change of kinetic energy, which is, how would you do that, right? You do 1/2 mv squared minus 1/2 mv squared. This is like the initial. Well, since that's 0, you can just kind of put that one off. And then you will have to move everything around to solve for the final velocity. So final velocity is the square root of 2 times the kinetic energy divided by mass. Okay, so you end up with the square root of 2 times this 31 joules, which is the total, divided by the mass, which is 10 kilograms. And all of that is under the square root. And you end up with 2.5 meters per second. Okay, so kind of a lot to consider with chapter 9 stuff, because you have to kind of think, okay, what type of energy is it? There's thermal, there's potential, there's kinetic. And then they throw in the word work. All right. So there's all these different symbols, and you have to figure out what's going on in the situation that you're dealing with. All right. So if we go on, so we've got power is the next portion of this PowerPoint. And power is the rate at which energy is done. So whenever you do a rate of something, you're taking it divided by time, essentially. And power is measured in units of watts. So if you go to the store and you buy light bulbs, you get them in watts. We do touch on, we'll get back to watts whenever we get into the electricity section in next semester. But, power is definitely involved with energy, so that's why we have to include it now. And a watt is a joule per second. So energy is measured in joules. If you divide that by time or seconds, then you end up with joules per second, which is a watt. Okay? And then this little guy right here, this 1 horsepower is equal to 746 watts. It is possible that you would need to have that to convert into horsepowers or from horsepowers to watts on a quiz or a test or even homework. Okay, so all right, so examples of power. So we talked about the light bulb, how you would go to the store, you get those, and depending on the intensity, would determine the wattage. Athletes, it's showing that they're converting chemical energy and fat into mechanical energy, which is measured in, it can be measured in horsepowers as far as power is concerned. And then it's showing this gas furnace, which is taking chemical energy into thermal energy. Okay, and so this is showing you sort of a dot product situation with power. If you have your and I said before that power was the rate of doing work, so work divided by time. And if a particle is moving at a velocity while acted on by a force, the power can be determined by the force times the velocity. And if there is any sort of angle involved, then you would do it, times the cosine of whatever that angle is as well. Okay. And if you think about force and velocity for a minute, a force is a newton and velocity is meters per second. A newton is kilograms times meter per second squared times meter per second. So right here, if you take this meter and you multiply it right there, then you're going to end up with kilograms times meter squared per second squared, which is a joule per second, which is a watt. Okay, so that's how you're still getting the same units. All right, this next one, this is sort of a lab that I would have had you do. It's a really easy one, and I still might have you do it. You might just have to go somewhere and find stairs. Now, obviously, I wouldn't want you to go anywhere public, just somewhere that you could, even outside, if it was just a few stairs at like a building that nobody's working at the moment or something, just drive around and get some fresh air for once. So this is saying 4 students run up the stairs in the time shown. Which student has the largest power output? Okay, so it's giving you these masses, all right? Now, we saw that power was equal to work divided by time. Well, work is force times distance, right? And are we given a force here? No, we're given mass. So remember, you can find force if you have mass by just multiplying it by gravity. So these are sort of the 3 ways that you can find power, okay? So that doesn't really answer the question. This is saying which student has the largest power. So if you take 80 kilograms, times 9.8 times this 10 meters divided by 10 seconds, I think you end up getting 784 watts. If you do the same one for this 80 kilograms, and it says that it's, A, B, and C are all the same height. They're all 10 meters. I think you would end up with 980 watts on this one. This one on picture C, if you do it, you should get 784 again. And then D, you end up with 627.2, I think. So picture B is actually creating the largest power. I just did the same math as I did for part A. All right. Trying to figure out how many. Oh, we're on the last one. We can get this done, right? All right. So this says a factory uses a motor and a cable to drag a 300 kilogram machine to the proper place on the factory floor. What power must the motor supply to drag the machine at a speed of 0.5 meters per second? And there's some more friction, and it gives the coefficient of 0.6. All right. So let's write some stuff down. We've got a mass 300 kilograms. We've got, it wants us to find power. It tells us that the machine has a speed of 0.5 meters per second, and that there is coefficient friction. So since it's moving with a velocity, then we're going to involve kinetic friction, okay, of 0.6. So, before we saw that there was a couple of ways to do power. Power can either be work